And that's the kind of picture you should have in mind for something with negative curvature. You know, something where in one direction things curve like this, in another direction it curves like that. Both these can happen in response to the matter energy fluctuations. And the analog would be to think of the saddle of a horse. Okay? Of course, when we're actually thinking in 4 dimensions, it's hard to give pictures. Because, I don't know about you, but I have trouble visualizing geometry in 3 dimensions. And I believe that it's impossible for human beings to visualize geometry in 4 dimensions. But you see, where imagination fails, mathematics prevails. So where you can't imagine that you can still write down equations and try to understand what happens using mathematics. That's a very good question. Okay, other questions? Please.
You said space-time curves.
Yes.
That raises the question of what does the curve include?
That's also an excellent question. Now, as you said, you know, you could take a 2-dimensional sheet in our 3-dimensional world and curve it. Okay, but you see, the mathematical theory of curved manifolds does not require the manifold that you describe to be embedded in anything. In fact, there are certain curved manifolds, and the universe might be one of those, in which the curvature is of a sort that cannot be embedded, at least in a low-dimension space. So, although to visualize this process, I asked you to imagine something curving in something else that is inaccurate. Okay? All that exists in the theory is the space. It's not embedded in anything else. And there's a way of mathematically describing it without having the embedded coordinates. And perhaps you could imagine that there is a globe without having anything outside, just a 2-dimensional globe without having anything outside. But I'm sorry, you see, the mathematics does not require you to have anything into which you're embedded, and that plays no role, so we excise it. There's nothing else apart from the manifold itself. Excellent question. Other questions, comments? Excellent.
Actually, what is this picture? Tell me in simple language, because it is like you are telling it very difficult language.
I see. What is the picture? You see, the space and time in which we live has a geometry that is different from that. That is, suppose you drew a triangle from here to the Andromeda galaxy, Andromeda galaxy to some other galaxy, and there to us. You added up some of the angles in the triangle, you will find that it's not 180 degrees. Not 180 degrees. Now, Euclid taught us, okay, that the sum of angles in a triangle is always different. But you see, Euclid was working in a mathematical system in which he was assuming certain things about space. For instance, he assumed the existence of parallel lines that never meet. That is not true of the universe. Okay? You see, mathematics is built upon certain assumptions. And the assumptions of Euclid for the real world are excellent on the scale of this table, but are false on the scale of the universe. Okay? So the geometry, you have to rethink geometry. All the geometry you've learned in high school, while excellent on small scales, is false for the universe on large scales. And the geometry actually not just is different, but it evolves in time in response to things happening. Okay, that's what this picture indicates. There's something happening, maybe there's a planet, and then the geometry is curving around in response to that. Okay, we can have more of this in the questions.
Just one thing. Would it be more accurate to say that it responds to things being rather than things happening, because happening would also be in time? Or
No, it responds to things both being and happening. You know, if you have a ball that's sitting there and a ball that's moving, the response to space-time is different. Yes. Okay, let's move on. So that's we tried to introduce dynamical space-times. Now, the title of my talk is quantum fluctuating or fluctuating space-time. I have to tell you about fluctuations, quantum fluctuations. So, very quick. We should move. Okay. So suppose we have a gun and two slits here. The first one, the second one, and a slit behind it. We have a gun shooting not bullets but electrons. Okay, something that's very small. That's the quantum size. And to start with, I block one of these two slits. You know, now the electrons go through the slit, perhaps hit the sides of these walls, do something, and then emerge at this other slit. And what we have is an experiment that measures where the electrons are recorded on the other slit. Okay? The question we're going to ask is, you know, every time you do the experiment, you get a slightly different outcome. That's not surprising, the electron moves a little differently. And this is a curve that tells you most of the electrons come here, few come there, almost none go here. Okay, so an intensity curve tells you how many electrons hit there divided by the total. Okay, if you perform such a thought experiment, this is kind of outcome you would find. Okay. Now, this I've said, and the reason, you might think that the reason that the electrons don't all come to the same place is because of some uncertainty in the initial velocity. Okay, slightly different initial velocities will let the electrons hit at slightly different places. Okay, now you might think the following, and everyone before 1900 did think the following. Now, this is all a matter, the fact that you get this curve, you can't predict exactly when the electron hits on the screen, is a matter of practicality. You can't get the electrons to go precisely enough in a given direction. Were you to be able to exactly tune the initial conditions of the electron, exactly set the initial condition of the electron to move in a certain direction, you would be able to predict exactly where the electron would hit on the far screen. Okay? This turns out to be wrong. Okay. It turns out that there is, that the right way of thinking of the world is given by what's called quantum theory, and quantum theory tells us, and there's enormous experimental backing for the statement, that no matter how carefully you measure the initial conditions of this electron, you will never be able to say for sure exactly where the electron will hit on the far screen. Two different electrons prepared in exactly the same initial state could, and in general will, hit that far screen in different locations. The best that physics can do is tell you about the probability of an electron prepared in a given state hitting somewhere on the screen at a given location. Nobody, presumably not even God, that's a joke, can tell you where any given electron in a given state. You know everything you can about that electron, and yet you cannot know for sure where it's going to hit on that other screen. All you can do is predict the probability of, you do the experiment 100 times, 80 times it's going to hit here, 2 times here, and so on. Okay.
So are you saying we can predict the probability?
Yes, we can predict the probability.
And the probability will be replicated.
Yes, if you do the experiment many times, you get the right curve. But you cannot, for any one event, predict certainty. There was a question here.
Yeah. No, I could not comprehend this part because that's what happens in television, right? It's basically an electronic shower on the screen.
Yes.
Can you see you can't predict the behavior?
Yes, you see, the question will be, to what accuracy can you not predict the problem? You see, suppose this curve is very, very small, over a very, very small region. Then it is true that electrons might go here or here or here or here. But if that region is nanometers, you don't care for the point of view of your television. And that's roughly what happens.
Okay.
Okay? It's a question of scales.
Are you saying that the single electron you cannot predict, but that we will know that the bulk of the electrons will come from?
That's correct. For any given electron, you cannot say exactly where. You know something about it, even for a given electron. You know that cannot be here if the probability is 0. And that's in response to your question. Okay, good. So physics, quantum mechanics teaches us that physics is fundamentally probabilistic. There's a fundamental uncertainty in the position of the electron and all other dynamical observables. Okay? The electron does not have definite position until measured. Okay? The state of the electron is in some sense a superposition of the electron being here with some probability and the electron being here with some probability. If you ask, where was the electron just before it hit the screen? There is no absolutely correct answer to that question. There's only a probabilistic answer to that question. I know it sounds weird, okay? It sounds weird to me, it sounds weird to you, it sounds weird to all the great physicists who invented quantum mechanics. But this notion was forced on us by experiment. It's the way the world works. Okay? The reason it sounds weird is that our intuition is built at a length scale where these effects are negligible. So this sounds non-intuitive. But it's true. Okay. We say the fact that we cannot predict exactly where the electron is. We use the words, some of us use the words, say that the position of the electron fluctuates. It's not certainly here or there. It's almost certainly in a little region. That's the bump shape I drew. But it could be anywhere within that region. The electron position fluctuates. It's not a certain definite position. Okay. consequences for experiment. I just want to show you in one quick slide how that works. You see, if we do this double slit experiment and we shut the lower of the two slits, as in the left slide, the one I showed you before, you get that kind of bump centered around the slit that's open. That's intuitive. Most of the electrons go through the slit and then a few of them get deflected. Similarly, if you shut the top slit and keep the second slit open, you get the second kind of bump.